We just did a brief review of lines and systems. We looked at how to graph y equals mx plus b and the two ways to graph from standard form. We also talked about the three different ways of solving a linear system. We know that solving a linear system means to find the point of intersection. So we looked at solving by graphing, where you look where the two lines cross on the graph. We talked about solving by substitution, where you have an x equals or y equals equation and you replace that variable in the other equation with what it's equal to. And we also talked about elimination, where you add the two equations together, and by making the coefficients of a variable the same number and opposite signs, you're able to eliminate one variable and solve for the other. Now let's go into a little bit more detail. If you have a question where you're asked to solve by substitution, you know that it's supposed to have one equation that starts with x equals or y equals. Now what if that's not the case? What if one of the equations doesn't start with x equals or y equals? Here's an example. 4x minus y equals -1, and negative 4x minus 3y equals -19. Neither of these equations start with x equals or y equals, but we still can solve by substitution if we'd like to. The way that we're going to do that is we're going to find a variable that's really easy to isolate, and we're going to rearrange that equation to start with that variable. And when you look in the second equation, negative 4x doesn't make it easy to isolate the x variable. And negative 3y also makes it kind of difficult to isolate the y. Isolate again means to get the y by itself or the x by itself. In equation 1, 4x is pretty tricky to isolate the x value, but we can easily isolate the y because it's just a -1y. So in order to rearrange that equation, we're going to look for a variable that's kind of already alone, that's all by itself already if possible. Usually there'll be one variable where that's the case if you're going to solve by substitution. So let's take our equation 1, let's rearrange it. Rearrange 1. And we're going to take that negative y, and we're going to say, okay, if we want to make it positive, the easiest way is just to move it over to the right-hand side. So we're going to move the -1 back with the 4x, and we're going to move the y to the right. That gives us 4x plus 1 because we have to change operations. This used to be -1, so it moves over, becomes plus 1. And it's equal to a positive y. That's our new equation 1. Equation 2, negative 4x minus 3y equals -19, doesn't need to be rearranged. All we need is one equation that starts with x equals or y equals, and we have it. So equation 1 tells us we're going to replace y with 4x plus 1. So to do substitution, all we have to do is find the y in equation 2. Here it is right here. We're going to cross it out. We're not going to use it. We're going to replace it with the 4x plus 1. So our substitution step is going to look like this. We're going to write down sub 1 into 2, and we're going to rewrite the second equation, but instead of the y, we're going to put some brackets. We're not going to forget this 3 because we didn't replace the 3, it stays. We just replaced the y with some brackets, and y is equal to 4x plus 1. So that's what our substitution step looks like. Now the rest of the solution is actually the same as the substitution that we did last time. We're going to distribute the -3 into the bracket. We're going to collect our like terms, and we're going to solve for x before we're able to substitute it back in and solve for y. I'm not going to complete this question here. I just wanted to show you guys that if you have a question where two of the equations, neither of them starts with x equals or y equals, you still can choose to solve by substitution if it's easy to rearrange for x or for y in one of those equations. Next, let's discuss what happens if you want to solve by elimination and you have to change two equations instead of one. So let's use an example. It's probably going to be the easiest way to talk about this. Here's a question that should be easy to solve by elimination, and we can use it to talk about the easiest method to approach this. 3h minus 4k equals 5. And 5h plus 3k equals -11. Here are two equations, and they both look like they're set up for elimination. You can tell because they have their terms lined up. So the h terms are lined up, the k terms are lined up, there's equal signs, and they're equal to the constant terms. So it kind of says elimination all over it. But when you look at which variable to eliminate, you have to consider them both and decide which one's the best choice. In order to eliminate the h's, looking at the h's, we know that we would have to get the same number in front of them and opposite signs in order to eliminate them. So we think to ourselves, okay, what's the same number that 3 and 5 both go into? What's the lowest common multiple of 3 and 5. A lowest common multiple basically just means if you did the 3's times tables and the 5 times tables, what's the smallest number they'd have in common? It's a multiple, so a number that you multiply to get, and it's common. It's the same for both those two coefficients of 3 and 5. In this case, it happens to be the product of those two numbers, so it happens to be 15. If we were to decide to eliminate the h's, we would have to get to positive and negative 15h. We'd have to have one positive, one negative, and they would cancel each other out. Now, if we wanted to eliminate the k's, we would have to look at the coefficients of k. We'd have to look at the negative 4 and the positive 3. And we'd say, okay, what are the multiples of 4 and 3 that they both have in common? What's the smallest number we could make them both equal to that would cancel them out? In this case, also, it happens to be the product of 4 times 3. It's not always going to be the product of those two numbers. For example, if you had, let me think, if you had a negative 3 and a positive 6, it wouldn't be 18, right? It'd be the 6 that they both go into. So it's not always the product, although that will work if you want to use a number that's bigger than the lowest common multiple as well. So looking at the h's and the k's, we see that we have to multiply both of the equations regardless of which variable we choose to eliminate. Now, I still think there's a better choice. They both require us to multiply both equations by something, but if I looked at this question and said, okay, which one would be easier, I would tend to go with the k's. The reason for that is because they're already opposite signs. So if I'm going to be multiplying both equations anyways, might as well make it a little bit easier and try to avoid any sign mistakes. I wouldn't have to multiply by a negative number if I were to eliminate the k's. So I'm going to choose to eliminate the k's, and when I do so, I'm going to write down what I want to get to on the top and the bottom of this little box here. Negative 4k and positive 3k. Their lowest common multiple is 12. So I want to change the negative 4k to a negative 12k, and I want to change the 3k to a positive 12k. I just kept the signs from the original equations, so negative 4 became negative 12, and positive 3 became positive 12. So how do I multiply my first equation to get to negative 12? If I have a negative 4 and I want to go to negative 12, I do that by multiplying by 3. So I'm going to take my entire first equation and I'm going to multiply it by 3. If I have positive 3k and I want to get to positive 12, that happens by multiplying by 4. So my entire second equation is going to be multiplied by 4. Now, what I'm going to want to make sure I do is I'm going to want to make sure I don't forget to multiply any of my terms by those 3 and 4. I'm actually going to write it in on the original equation. So next to every single term in my first equation, I'm going to write a 3 because I'm multiplying that whole equation by 3. The most common mistake is to forget to multiply those terms by whatever you're multiplying the equation by. So I'm going to multiply my second equation by a positive 4. I'm going to write the 4 in next to my second equation so I don't forget. There we go. And I'm just going to change both equations. So 3 times 3h is 9h. 3 times negative 4k is negative 12k. And 3 times 5 is 15. That's my new first equation. For the second equation, 4 times 5h is 20h. 4 times 3k is a positive 12k. And 4 times negative 11 is negative 44. We talked about this in class. I reminded you to check two things. Not sure if you remember what they are, but the two things I want you to check is I want you to check opposite signs. So make sure that when you change your equations out, you've got plus and minus right there. And I want you to make sure that you check that the last terms were multiplied. Multiplied. So I did multiply those two last terms. They're not a 5 and an 11 anymore. Now they're 15 and negative 44. So we've done those two things. We checked our checks. Then we have to say, okay, our 2k's can be eliminated by adding the equations. This is normal elimination. 9 plus 20 is 29h. The 12's disappear. And 15 minus 44 is negative 29. Check your signs when you write these answers down. The number that's the biggest number, 44 in this case, has a negative sign, so my answer should be negative. And that just means that h is equal to negative 1. And we're halfway done the question. Now, I'm not going to finish the rest of this question because we've already done an elimination example in the previous part of the review, but I did want to show you that you can multiply both equations to eliminate a variable as well. Now, what happens if you get a POI and you want to check to make sure it's correct? Sometimes I might say, okay, is the correct solution to this linear system -1, 4, for example? The question I just did, is it -1, 4? Okay, so we're going to see if that's correct. How do you check an answer? How can you make sure that your POI is correct? Well, the way you check if any point lies on any line is by doing a left side, right side check. So with a linear system, it's the exact same thing. You're going to do a left side, right side check with both of the original equations. So these two equations here are my original red equations. Those are the ones I'm going to use for my check. So let's move this down a little bit. In order to check your solution, we do a left side, right side for, that's not how you spell for. What's going on here? For each original equation. So for each original, in huge letters because it's very, very important, equation. So my first original equation was 3h minus 4k equals 5. And my second original equation was 5h plus 3k, that doesn't look like a 3, equals -11. So I'm doing two separate checks here, left side, right side for each one. I'm going to substitute my values that I'm checking in for x and y. If the question I'm asking myself is the answer -1, 4, that means I'm going to substitute -1 for the x values and 4 for the y values in each of these left side, right side checks. So in this case, they're not x's and y's, I understand that, but they're alphabetical order still. So we're going to assume that h is our x and k is our y because when we write our variables, they follow alphabetical order. So in this case, let's check for h is equal to -1 and k is equal to 4. So we substitute them into the equation. 3 times -1 minus 4 times 4 should equal +5 if it's correct. Ooh, that was cool. We follow BEDMAS when we do our checks. Very, very important. So -3 minus 16, oh dear, that's not equal to 5, is it? So -19 and 5 not quite equal. Let's check the second equation. So 5 times -1 plus 3 times 4, -5 plus 12, that's equal to 7, again, which is not equal to -11. So since the left side does not equal the right side for both, and it's for both equations, that's very important to state unless you want to do two separate left side, right side statements. For both, therefore, the POI, this is not working, let's try again. The POI is not -1, 4. That's how you can check any of the answers. And if you've done your substitution or elimination correctly, then both sides will equal in each equation. It will be 5 and 5 and -11 and -11. I just picked a number out of the sky, so obviously the -1, 4 is not correct. Finally, we're going to go over the different types of word problem questions that you can see in this unit. We'll talk about, first of all, how to solve a word problem question, what the steps are to looking at word problems. And the second thing we'll look at are the main types of word problems that people had trouble with. These are going to come out of the 1.5 section of the 2D textbook. And we'll talk about the ones that were more difficult and just remind you how to approach those questions when you're setting up your equations. So with a word problem question, you're going to follow the same 4 steps every single time, no matter what the word problem says. So the first step is going to be to write your let statements. Now, with the let statements, it might be hard to find out what you're trying to say, what you're trying to make them represent. But if you look at your last sentence or look at the very end of the question, you should be able to see what we're asking. So the last sentence might say, how long did we have to drive the car for the cost to be the same in both rentals? So you're going to look for the last sentence to tell you what you're trying to find, and that's how you're going to make your let statements. With your let statements, you're going to make sure that you are specific. So not let T represent t-shirts. Let T represent the number of t-shirts sold or purchased. Okay, be specific. And when we're talking about being specific, we're going to look at number of, cost of, price of, amount of, words like that. Okay, not just t-shirts or balloons or whatever we're trying to find. Also include units, so in kilometers, in meters, in dollars. That's important for full marks for your let statements as well. Now the second step to solving a word problem question is to create your equations. And that tends to be the one that students have the hardest time with. So create two equations. It's important to remember that each equation that you create should have one of each of the variables in it. So two variables in each. If your variables are x and a y, each equation should have an x and a y in it. Now most equations are created either by sentence or by idea. That's kind of a first go-to method to creating your equations. So by sentence is when you have a paragraph, your whole question's in a paragraph, and it gives you all the information for one equation in one sentence, and the next sentence is all the information for the second equation. So for example, you and your friend go to the store, you buy, I don't know, sandwiches and cans of pop, and it costs you a certain amount of money, and they talk about your friend paying a different amount of money for a different combination of pop and sandwiches. Those would be an example of by sentence, where your first sentence talks about your whole purchase, and that's one equation, and the second sentence talks about your friend's whole purchase. That would be a different equation. And there's a bunch of examples in the textbook of equations by sentence. I'll just pick one here, page 41. Example, it could be number 15. Talks about vegetarian and roast beef sandwiches, two different orders at two different costs, and that's an example of creating equations by sentence. Now the other one is by idea. By idea tends to be a little trickier. You look at the question and you're not quite sure where to go with all the numbers given to you because they're dispersed throughout the question. If you look at all of the numbers, and they're all kind of referring to two main things. So maybe half the numbers talk about money and the other half talk about the number of items. For example, we talk about going to the school play. We're selling tickets to the play. And we might talk about the cost of a student ticket and the cost of an adult ticket and the total proceeds earned by selling tickets for this event. Those numbers would all be dollars. They're all talking about money. But then we might also say altogether we sold 150 tickets and there were 3 times more students than there were adults. So those other numbers refer to the number of tickets. And so those are the two main ideas, and you would create one equation for each idea. Example in the textbook, page 40, number 8. Page 40, number 8 is an example. When you look at number 8, it talks about selling baseball gloves and baseball bats. They give you the costs for a baseball glove and a baseball bat, and they tell you that this employee sells $647 altogether. So those 3 numbers are referring to money. So there's going to be one equation that's just a money equation talking about how much money they have made by selling baseball gloves and bats. And it also says that he sells 28 items altogether. So the bats and the gloves added together, B plus G or whatever letters you pick, would equal 28. And that's a number of items equation. So we have one equation for the cost, one equation for the number of items sold. And that's the two main idea thing, where you're looking at equations, one for each idea. Now, how to create your equations for specific word problem questions we'll discuss afterwards when we look at the very specific types like the distance time equations and things like investments and stuff like that. We'll go over that afterwards. The third step to solving a word problem question, once you have your 2 equations, then you know how to do it. It's just solve by substitution or elimination. And we talked already about how to pick which method to solve with. You're going to solve by substitution if an equation starts with an x equals or a y equals, or it might be C for cost, for example. And you're going to solve by elimination if the order is all the x's, all the y's equal the numbers, if the order tells you that you're going to be working on elimination. And finally, you're going to create a therefore statement that is relevant. That means not therefore the POI is, but therefore Billy Joe sold however many adult tickets and how many student tickets for the concert. So relevant. Let's spell properly. Okay, so those are the 4 steps to solving a word problem question. Now let's talk about the very specific word problem questions, the things that you need to remember that you might not remember from the lessons in class, because it's been a little bit of a while. The trickier questions, the ones you need to remember, are the comparison questions. I don't know why this is not writing. Let's try again. The comparison questions are things like we sold 3 times as many student tickets as adult tickets. That's an example of comparing. So you could have comparison type questions, and my advice to you for that was to draw the piles. So let's say we said 3 times as many adults as students. If you pictured all the adult tickets in a pile and all the student tickets in a pile, these are the adult ones and these are the student ones, because 3 times as many adults means adults were the bigger pile. Which pile would we have to multiply by 3 to make them equal? We have to multiply the student ones by 3. So this equation would be A equals 3S. So comparison types of questions tend to be a little trickier to create the equations, but draw the piles to help you to figure out which one you have to multiply or which one you have to add. Remember, things like more than or less than means you're adding or subtracting, versus times would mean you're multiplying. If I said there were 5 more males than females in the room, 5 more males than females, that means there's more boys, so males is over here and females over there. So if it's 5 more, that means I'd have to add 5 to the girls to make them equal. So it would be M equals F plus 5. So that's an example of comparison type question, and that's one of the ones that you kind of need to keep in the back of your mind when you're doing word problem questions to make sure that you know how to create the equations for those. Second type that we did that was kind of a different type is the investment questions. And investment questions looked at putting a certain amount of money into 2 different accounts. And I don't usually tell you how much money goes into each account. So if I have $5,000 and I want to invest it into 2 different accounts, I would probably pick X and Y for the amount going into each account, because I don't know how much I put in each one. And I might tell you that this account earns 2% interest and this account earns 1.5% interest. So when we're given percentages, we make sure that we change them to decimals, and so we divide by 100 to make it into 0.02. 1.5 divided by 100 is 0.015. And I might tell you that all together in 1 year I made $45 in interest. I know our examples in class from the textbook are a little bit older. They claim to make $800 in interest. So I would tell you that in the real world that doesn't really happen in a year, but so $5,000 goes into 2 different accounts, one at 2%, one at 1.5%, and you make $45 altogether in the year. I'm just picking these numbers, so they might not work out if you finish the question, but I wanted just to show you how to create the equations. Okay, so let X represent the amount invested at 2% interest, right? The amount in dollars. So when you're writing out your let statements, make sure you're specific. Let X represent the amount of money invested at 2% interest in dollars. So that's an example of a let statement for this type of a question. And when I'm looking at creating my equations, I'm going to say, okay, what does all these numbers represent? What do the numbers show me in my little diagram that I made out of the question? And I recommend that you make this diagram because it's going to help you to make the equations. X and Y has to show up in both equations. So that's kind of like the dividing line. All this stuff over here has to do with money that I invest. So money going in. And all of this over here has to do with money going out. So those are my 2 main ideas. I'm going to have a money in equation and a money out equation. And that's going to help me to create my 2 equations for this question. So for my money in equation, obviously you'd have another let statement right there. I'm not going to show you them both because you guys know how to do them by now. So money in equation says that my 2 accounts add up to $5,000, and a total always goes at the end. So that's my money in equation. My money out equation has to also have an X and a Y, but now I'm multiplying them by the interest. So 0.02x plus 0.015y, those add up together to get me $45. So this is my money out equation and my money in equation. If you have an investment question that has decimals right here and you want to get rid of the decimals, then you can just multiply by 1,000 in this case, because I have 0.015, 3 decimal places to get rid of in that example. If it was just 2 decimal places, I'd multiply by 100. The number of zeros you multiply by should correspond to the number of decimal places you want to get rid of. And make sure that you multiply the 45 as well. So if I was going to multiply this equation by 1,000, it would be 20x plus 15y is equal to 45,000. I don't know why this is not writing properly, sorry guys. Okay, so that's how you work out the questions to do with investments. The next type of word problem question that was very specific dealt with motion. And those are the distance time questions. You were flying an airplane against the wind, or you were paddling a canoe against the current. Anything that had to do with movement and some kind of a motion that was controlled and some kind of a nature that was out of your control. So anything to do with distance and time, distance, time was usually a motion type of a question. And those questions are based on the fact that distance is equal to speed times time, where your speed is made up of you and nature. And in two different situations, you're either going to be going with nature or you're going to be going against nature. So things like paddling upstream or downstream. Downstream is with the current, so you're adding, and upstream would be against the current, so you're subtracting. And so one equation is going to have a plus sign and one equation is going to have a minus sign, and those are going to be in the brackets when you combine yourself and nature to create the speed. An example of a question like this is on page 44. And we talked about the downstream and upstream. So it says down a river. That means you're going with the current. So we have paddling speed and speed of the current. Those are the two things they're asking you to find. So this question would start by writing a let statement. Let C represent the speed of the current in kilometers per hour. Make sure that you include the units. And let P represent the paddling speed in kilometers per hour. So make sure your let statements are there as well. Let P and C, and make sure it's in kilometers per hour. That's your speed. So in this first equation, it says we're going down the river. So we're going to add our paddle plus our current. Make sure that when you're adding them and subtracting them together, the strongest force is you, so that goes first. The paddling speed, your motion, is going to go first, and nature is either going to be added or subtracted to you, not vice versa. So that was the first equation, and the second equation said the return trip against the current took 3 hours. So we're going to return the same distance, and in this case it's going against the current, so we're subtracting the current, and it takes 3 hours. So creating that equation, just basically you have to make sure that you know when to subtract and when to add, and that you remember the format for the equation, but other than that it's given to you in the question. The tricky part about these was to remember how to reduce it. You don't want to do more work than you have to, so the easiest method is to get rid of the 2 and the 3. Get rid of your time by dividing both sides of the equation by that time. So equation 1 would be 6 equals P plus C, and equation 2, once we divided both sides by 3, would be 4 equals P minus C. And those would be the two equations that you're going to use. Now looking at the equations, they're both variables added together equal numbers. So that says right away you want to use elimination, and when you use elimination, those C's are going to cancel out because we have plus C and minus C, and when you add them together you're going to be left with 2 P's. So here's what it would look like. You would add together these two equations, equation 1 and equation 2, those would cancel and you would get 10 equals 2p, because 1p here and 1p there give you 2p's. That's a common mistake, so be careful. So that means that p is just equal to 5 kilometers per hour. So you substitute that back in and you get your current speed. So that's the second kind of very unique type of word problem question. The final one has to do with mixtures. And so the last types of questions were mixture questions, where you had to figure out the percentages and figure out the volume of each type of solution used. So mixture examples are found on page 45. There's one at least on page 45. Very, very, very similar to the investment questions in terms of how you're going to create their equations. There's only one little difference. So let's look at an example on page, it's called example 3 on page 45. It says Miriam has a bottle of 5% acetic acid. This is 5%. And a bottle of 10% acetic acid. So I'm drawing my picture because that's really helpful to create the equations. How much of each should she use to make 250 milliliters of 8% acetic acid? So I draw the picture because it helps me to visualize what I'm doing. I don't know how much of the 5% and how much of the 10% Miriam's using. So I'm going to use that for my variables, x and y. So my let statements should say let x represent the volume, or the number of milliliters has to do with the amount of solution, right? The volume of 5% acid used, and the volume is in milliliters. Make sure that you are specific in your let statements. Let y represent the volume of 10% acetic acid used in milliliters. Okay, so when you look at these questions, sometimes it seems hard to differentiate between what goes in the first equation, what goes in the second equation. This is an example of a by idea. 5, 10, and 8 all have to do with percentage or concentration. So when we make our equations, we're going to make one equation that has to do with the concentration. And then the other numbers, the 250, just is volume. So we're going to have one equation that has to do with the volume and one that has to do with the concentration. So the volume equation is easy. That one's just x plus y equals 250. Okay, this concentration equation, you have to remember to multiply the percent times the amount. Always percent times the amount. All the way through the equation, even in your total. Even at the end, it's the percent times the amount. So we're going to say 5% is 0.05, 10% is 0.1, and 8% is 0.08. So when we write our equation down, we're going to write down 0.05x plus 0.1y equals, in our final total, we have to still multiply percent times the amount. So it's 0.08 times the 250. This is the one spot where people forget to multiply and run into difficulties. Percent times amount, percent times amount, percent times amount. So the next step in this question would be to expand and to simplify these two equations. The first equation is going to be x plus y equals 250, and the second equation would be 0.05x plus 0.1y equals, now we multiply the 0.08 times the 250 and we get 20. So those are our two equations. Just like last time, we can choose to eliminate these decimals by multiplying by 100. We don't have to. You can easily do elimination by working with the decimals if you want to. If you wanted to eliminate by keeping the decimals, you would want to multiply this equation probably by negative 0.1 to eliminate the y's. Alternatively, you could multiply by negative 0.05 to eliminate the x's, or you could just multiply the whole second equation to get rid of the decimals and start with that. Solving by elimination is the easiest method here because they're lined up, but if you prefer to do substitution, you can choose to isolate the variables in the first equation. Either you make it x equals or a y equals equation, and then you substitute it into the other equation to solve. The complete solution, again, is on page 45, but I wanted to go over how to set up these mixture examples because they were very unique in this unit. Remember that you can check any of your answers by substituting them back into the original equation. So a left side, right side check goes a long way to checking to make sure that your solutions are correct. Remember to always give units in your let statements and to always be very, very specific in your let statements. Solving graphically can also be checked by doing a left side, right side check with both of the original equations. So that's the entire unit on lines and systems. Good luck with your studying, and you can look at chapter 1 in your textbook to see some examples in addition to the ones I've shown you. Look at the examples in the book, look at the solutions, and look at the notes at the very top or at the sides of each of the sections to help you remember what to do.